Okay, so in this lecture we have a fluid problem, and we are trying to solve this fluid problem by using the domain decomposition method. And the mathematical form of this fluid problem is, you can see here, we have a PD in this case, and this we are trying to solve this PD by using the previous domain decomposition method, in which in previous lecture we solved the linear partial differential equations by using the concept of the domain decomposition method. And here in this lecture we are also trying to solve this PDE, the second order PDE, using the concept of the domain decomposition method. First of all, we want to know that what is exactly this physical shape, and then how we can model this physical shape in a mathematical language. And once we have that mathematical language, then how we can solve that mathematical form along with the initial and boundary conditions by some exact or approximate or asymptotic method. So the method here is, once again, the ADM method. So first of all, let me explain the physical shape of this problem. This problem is called the Stokes first problem, and it was introduced by Stokes in 1851. And one interesting thing is, this problem is still unsolved by a domain decomposition method. So you can say this is a research problem for you people. So uh, uh, try to solve this problem by ADM. So those who solve this problem, that will be a kind of contribution in the field of fluid dynamics by using this ADM method. So uh, try to think, try to to observe that how we can use this method for the solution of this PDE. And once you successfully solve this problem, so we can also uh, put this calculation somewhere in a good journal. So it's a kind of new problem for you people. So we'll try to solve this problem. Okay, so the fluid phenomena is, we have a flat plate, and the fluid uh, initially at rest uh, on this flat plate. And this is the configuration of this fluid profile, where x-axis is along the direction of the fluid and y is perpendicular to the direction of fluids. So at time t power t equal to 0 plus means when the time is about to start, the plate starts moving. The plates starts moving in x direction, and that is exactly this diagram. So at time t equal to 0 plus, the plates starts moving in x direction with constant velocity v. Uh, we also assume that the pressure gradient partial p by partial x along x axis and the gravitational force along x axis, they are 0 in this case. So now the question is, if we have a scenario like this one, that initially a plate was at rest, and after some time t, the plate starts moving along the direction of the fluid. So how we can model this physical shape in a mathematical form, and then how we can solve that mathematical form by using some series method like ADM, or any other numerical method. So let's see what happening here. So if you look at this physical shape, if we revise the previous lectures, the velocity profile in this case is equal to, since the flow is along x direction, so u is a function of uh, x, and t is also considered here. The time change is also we are considering here. So u is a function of xt, and the remaining two terms are 0 in this case. So this is exactly the velocity profile for this fluid phenomena. Now, is we know that uh, we have some we have two fundamental equations. One is called the continuity equations del dot v, which is equal to 0, or the divergence of v is equal to 0, and the second fundamental equation is the the conservation of momentum, in which you can write that equations rho dv by dt, where v is the velocity of the fluid, dv by dt is equal to minus pi, where p is the pressure of the fluid, I is the identity tensor, plus del dot tau, yeah, the divergence of the Cauchy stress tensor, plus the body force. So this is called the conservation of momentum for in fluid dynamics. So this equation is identically satisfies. So we can see here partial u by partial x is equal to, this is partial y, this is partial y, change occur along y directions, y coordinate. The fluid flow, the direction of the fluid flow is along x axis, but the change occur in y direction, and you can see here from this diagram that you have a parabolic profile like here. Once the fluids, the particle of the fluids, once the plate start moving with uniform velocity v, so the profile will be exactly like this one. So you can see here the inertia basically created in this physical shape, that for example if the particle here is at rest, and once this plate starts moving, so basically all the particle adjacent with this particle, they starts moving, flowing like this one particle is sliding on another particle, and this backward parabolic visuals you can see here can be created in this form. So once you apply all this velocity profile on the governing equations, like on this equation and on the conservation of momentum, we will have exactly this form, and this is called the second order partial differential equations, in which u is a function of t is equal to, this is basically nu, which is equal to rho by mu, the ratio of the density and the coefficient of viscosity is called the uh, kinematic viscosity of the fluid, and the second derivative of the velocity of the velocity component of the fluids, or the unknown functions u, which is depending on x and t. So this is called the linear second order partial differential equations, along with this initial as well as boundary conditions. So you can see here. So now the question is you revise your previous lecture, and in previous lecture we already solved some system of linear PDEs by using the ADM, So here exactly in this case, if you look at this problem, we have two operators in this case. One is the partial by partial t, which is called the linear operator in t, which is a linear operator, and the second operator is again ly, you can say lyy, and this is lt, and this is equal to partial square by partial y square. This is another linear operator which is second degree linear operator, and we also assume that these linear operator are invertible. So this is exactly equal to, the L inverse is equal to, for this linear operator in terms of time, is equal to this dot dt plus, and this the inverse of this linear operator is equal to L inverse for that linear operator is equal to the double integral of the unknown function u, which is depending on xt, dy by dy into dy. So these are the invertible linear operator. So now what exactly ADM uh, 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 process this PDs. So we rewrite this partial differential equations in operator form. So the first operator form will be like this one: L of u of x, this is u of xt, and you can say this is LT of u, which is because this linear operator is depending on t, or the linear operator for t, and this is nu, which can be written like this one, the linear operator, uh, which is Lx, yeah, Ly, you can say u of xt. So this is the operator form of the above equation. Next we have uh, we want to apply this Ly, the inverse of this Ly, on both sides of the equation. This L inverse on both sides of the equations. So this will be equal to, if this equations can be written in this fashion, that if we apply this invertible operator on this linear operator, so they are identical, their answer will be identity, and u of xt is equal to 1 by nu, which is a constant term, L inverse LT, this is L inverse of y, of the unknown function x comma t. So this is exactly the invertible form of the above partial differential equation. Now what we are doing here, we want to integrate this, and you can say, you can see here, the we need the zeroth order solution in this case. So this d square u by dy square, we can say this is equal to 0, because if you revise that lecture, we can see in that lecture that the zeroth order solution is equal to the function value plus the source term of the partial differential equations. But in this case, we do not have any source term and there is no function value, so this is equal to 0. And once you integrate this two times and after applying the boundary conditions, the answer is equal to u naught is equal to v, small v. So here uh, this is the solution of u naught, and all other terms can be written in a recursive form, uk plus 1. Okay, let me write here uk plus 1 uh, is equal to 1 by nu double integral of lt means partial uk by partial t dy by dy into dy, because the invertible operator is in terms in y and where k is greater than or equal to 0. So this is exactly the recursive form of the above partial differential equations. Now for k is equal to 0, this form is equal to u1 is equal to 1 by nu double integral uh, partial u naught by partial t dy by into dy. Okay, so now we have partial partial derivatives with respect to the unknown function has partial derivative with respect to t, and here is integration is in terms of y. So can we use the fundamental theorem of calculus in this case? This is your homework. See what is exactly the fundamental theorem of calculus for integration, and then see exactly this scenario and use that theorem in this case, and I'm waiting for the solution of this u1, that what is exactly the solution will be the solution of this u1. So this is your homework. Okay, thank you. See you inshallah in next